Okay, we will start today samarium neodymium isotopic system. So you can remember rubidium strontium isotopic system we completed last week, and I told you that there is some kind of opposite behavior of samarium neodymium isotopic systematics. Okay, because the difference is because of the incompatibility. Okay, in the samarium neodymium system and rubidium strontium system, the difference is basically coming from the incompatibility because the parent daughter incompatibility is important, right? In the rubidium strontium system, rubidium is more incompatible, right? Rubidium is more incompatible uh, than strontium. Remember? So that's why in melts, for example, continental crust, which is formed as part of the melt, right? Produced after partial melting, contains a lot of rubidium. So over the time, after many million years later, you have a lot of strontium isotopic composition as a result of rubidium decay, right? If you have high rubidium, then you will have a lot of strontium, radiogenic strontium accumulated over time, because rubidium is more incompatible. So that must have been accumulated a lot in the melt in that case, right? Because it's incompatibility. But in the case of samarium neodymium, neodymium is the most incompatible element, right? So in this case, the daughter is more incompatible than the parent. In the rubidium strontium system, parent is more incompatible. So that's why you have a lot of strontium remaining in the strontium accumulated in the rock later on, if it is a product of the melt. But in the samarium neodymium system, the difference is neodymium is more incompatible. That means daughter is more incompatible. So in a melt product, you don't have much parent accumulated, right? So if you don't have much parent there accumulated, its radiogenic daughter will be less over the time. Okay, if you don't have the parent isotopes, you don't have many daughter isotopes with time, because radiogenic decay, there is not many parent isotopes to decay. So in that case, for melt products, you don't see high neodymium isotopic composition, uh, unlike in the rubidium strontium isotopic system, right? So therefore, just remember these two isotopic systems behave differently, right, in opposite ways in terms of uh, incompatibility of these elements, right, parent daughter elements. uh, before we discuss much more details on that, just look into this diagram. What is this diagram? What does it mean? This is the rare element diagram, right? Rare element plot. Rare element plot. So you can see the rare elements are there, starting from lanthanum. This is lanthanide series, okay? Starting from lanthanum to lutetium, right? So in the rare elements, we make these diagrams. We plot these rare elements in this diagram in a way that the more incompatibles are arranged in this direction. Okay, so if you compare two elements, given elements in this rare element diagram, whatever the two elements, the left hand side element should be more incompatible than the other one. Okay, so always remember, the left hand side is more incompatible than the right hand side. So if you consider the relative incompatibility, whatever the couple of elements that you are considering, the left hand side one will be more incompatible. Even if you take two elements like here in the right hand side, so these are the least incompatible elements. Okay, because it is right, they are located in the right hand side, but still if you want to compare their relative incompatibility, these two, you will see the left hand side element, this one will be more incompatible than the right hand side element. Okay, so anyway, generally the more incompatibles are coming on the left hand side, and the less incompatibles are coming on the right hand side. So in other words, uh, the compatible elements compatibility increases oppositely, in opposite way. Okay, right. So this is just the behavior of rare elements, and how we represent them in rare element diagram. So you can see here neodymium lies in this series here, whereas samarium is here. So obviously you can understand now neodymium should be more incompatible than samarium. Okay, so if you can remember this Rath element plot, you can easily remember the daughter is more incompatible than the parent. Okay, so in Rath element plot, this can be easily recognized. And I think those who are doing the igneous petrology, advanced igneous petrology, knows about these characteristics of rare earth elements. But in any case, I just want to remind you, rare earth elements are less abundant in rocks, right? I mean, they are rare, so that's why we call them rare. And also, we were unable to measure them until the mass spectrometer was developed, right? Because we had only XRF technique. XRF cannot measure rare earth elements because their concentrations are so low. That's why we call them trace elements or rare earth elements. Okay, and commonly they have +3 valency, right? Their valency is 3 plus, right? And you can remember all the rare earth elements, right? Not just a few of them. All the rare earth elements have 3 plus, but there are some other varieties also. I mean, some other species also there available. For example, europium. They are it's europium 3 plus is common, but there are some europium 2 plus occurrences also, right? For europium, that is another feature. Okay, and but for plagioclase, we talked about europium uh, attraction to plagioclase, right? Remember, that is 3 plus. Okay, mainly europium 3 plus, the common rare earth element. And this is cerium, right? Cerium, you have tetravalent also, right? 4 plus. Those are some additional varieties, but commonly they are 3 plus, the 3 plus in valency. So in general, REs are incompatible. All the REs prefer melt, but relatively, if you consider their relative incompatibility, that increases in this way, right? From right to left. That is the case, right? And here again, you can remember the neodymium prefers melts more than samarium. So that's why we have a lot of, less neodymium isotopic signature in melt derived products, unlike rubidium strontium system. There, strontium is high. Strontium isotopic systematics will be showing higher ratios due to high amount of parent rubidium availability. But here, low amount of parent availability, that is samarium availability in melt, shows depleted isotopic neodymium compositions. Okay, so we can interpret this in different ways. So you always remember, if parent is less, then your daughter will be low in that particular rock. So that is important to remember. And the second plot here shows you some trace element patterns or earth element patterns of common reservoirs. For example, you can see the chondritic composition. Okay, the chondritic composition, uh, but it is normalized to chondrite composition, right? I think you can remember those who did the advanced igneous petrology. What we did about this, we talked about this normalization, right? If you normalize something, any value from your sample, I mean, the values of your sample divide by a chondrite value, we call it chondrite normalized uh, pattern, right? When you plot this in a diagram, in a logarithmic diagram, right? So for earth elements, normally we take chondrite as a standard, right? To normalize, to divide, right? So chondrite composition divided by chondrite composition is always giving you just one, right? Number one, the value is one. So that's why for chondrites you have this type of constant composition, right? So this is the chondrite composition, and then you can have upper continental crust. This one, this is upper continental crust. There, earth element pattern shows. Sorry, earth element pattern shows some variation of uh, light wrapped element. I mean, uh, some light wrapped elements are enriched pattern is shown there, right? You can see relative to the heavy middle to heavy earth elements, right? These are middle and these are heavy earth elements, right? These are middle earth elements. So middle to heavy earth elements, uh, relative to those, light earth elements are enriched. Why? Because continental crust is a product of partial melting of mantle. That means it is the melt derived product, right? So in a melt, you will definitely see rare elements are enriched. I mean, light rare elements are enriched because light rare elements are more incompatible than middle to heavy rare elements. Therefore, definitely you must see a pattern like this, right? Light rare elements enriched pattern. And mid-ocean ridge basalts, these are direct results of partial melting of the mantle, right? So it is almost like uh, it's almost like the mantle because it is a product of depleted mantle. So in the mantle, you always get less amount of incompatible elements because why you get less amount of incompatible elements? Because mantle melting already contributed to the continental crust formation. So therefore, light trap element depleted pattern will be showing in your mantle product, right? But this is basalt, mid-ocean ridge basalt. Okay, it is again melt, right? It is again melt, but if you compare the mob composition with the depleted mantle, then you will see the pattern will be identical with the depleted mantle pattern, but the uh, relative composition uh, will be uh, lower. Abundance will be lower because it is a residue. Residue contains less amount of rare earth elements. So therefore, you will see a gap of trace element composition between the depleted mantle and the uh, mob. Okay, depleted mantle and the mob. Okay, depleted mantle and mob. So this difference you have to understand, but in general the pattern is same. The pattern should be very similar, only the only concentration gap is there, right? So just note this down, these features, these are important. All right, so this is about the incompatibility, and you have to remember that all differences between the two isotopic systems, right? Okay, so in the case of the pattern, the rare earth element pattern of the depleted mantle and mob, you have to remember this because the shape is almost same. Okay, the shape is almost same. That means the incompatible elements are depleted, but the relative composition between the two is different because depleted mantle is a residue. Okay, it's a solid. So always overall rare earth elements will be low in the residue because overall rare earth elements are all the rare earth elements are incompatible. Okay, so anyway they prefer going into the melt. So therefore definitely you will see higher composition in abundance, higher abundance in the melt produced there. However, the light rare earth elements are more incompatible than the heavies. Therefore you will see an opposite pattern to the continental crust, because this is the continental crust pattern. For the mantle, it should be the opposite pattern. But the mob, being the melt produced from the mantle, again will have same pattern, but little enriched in their abundance. Okay, there will be a very big difference between the continental crust and mob and depleted mantle in terms of the abundance. So you can see here it's a logarithmic. Okay, it's a logarithmic abundance, difference. So therefore it's not a small difference, even though it's closely located there, right? uh, in the case of average shale, its shale is also there because there are a lot of sediments associated with a lot of continental fragments, and this shale or the shale can be represented as the average sedimentary composition in our crustal environment. Okay, they contain because these sediments are mainly derived from continental crustal material. So continental crust is anyway enriched in light rare earth elements. So the shale will also be enriched in light rare earth elements. And the abundance, if you take the relative abundance between those two, will be higher because the shale represents the eroded material from the continental crust, and it accumulates more and more rare earth elements in that case. Okay, coming from the continental crust. So therefore you will see this type of a difference. But heavy rare earth elements, there will be no big difference, although it is very close to the mob composition. uh, uh, Light rare earth elements are very much enriched in the shale composition also, right? But shale, for the time being, you don't need to consider much because we are not using that in our discussions. You can just remember about the variation on the other terrestrial reservoirs, right? We call these terrestrial reservoirs continental crust, mid-ocean ridge basalts, depleted mantle, chondrites. No, sorry, no, chondrite is not considered as a terrestrial material, terrestrial reservoir, but it's the source of the planetary bodies anyway. Okay, so these basic features you have to remember when we study about these isotopic systems. That is important. So let's move directly now to the samarium neodymium decay scheme. There we have two isotopes. Okay, this one and this one. So what is the parent? Samarium. Neodymium is a daughter product. So 147 samarium decays to 143 neodymium. So if you consider the isotopic abundance of 147 samarium, it's about 15%, right? In addition, there are 4 other isotopes in the samarium family, right? And 143 neodymium, you can find about 12.2% globally in planetary materials. And there are 6 more isotopes of neodymium, right? In our situation, we are using these two isotope isotopes as parent and daughter. And to get the ratios, like in the rubidium strontium system, you can remember we divided these parent daughter isotopes by a stable isotope, right? Remember 86 strontium, like that. Here also we will take a stable isotope of neodymium, because we have to take the one of the stable isotopes among the daughter products. Okay, so we will take 144 neodymium for that case. We will see that later. Right, half-life is 106 billion years in this scheme. 106 billion years, right? Very, very long. So that means our Earth is how much? The age? 4.5 billion years. Okay. So it's just very tiny bit of this half-life of this samarium neodymium system, right? So you can imagine how much samarium is still left in our planetary materials in the planet, right? To make it 50% decreased, the budget, initial budget, to make it 50% decreased, you need to pass 50 billion years at least, right? 53 billion years, right? But we have still lapsed 4.5 billion years. So that means huge amount of samarium, uh, which was available at the time of formation of the Earth, is still remaining, should be remaining in our rocks, in our planet, right? Some of the samarium neodymium ratios. This ratio is important because this is the one that determines how depleted or how enriched your product is, right? Because if you have less samarium, uh, less amount of samarium, definitely you will have less amount of neodymium. Therefore, you will have a depleted isotopic composition in your rock, right? But if you have a high amount of samarium, uh, that means high amount of samarium neodymium ratio resulting, uh, you will have high amount of neodymium daughter products as well. So that means your rock will be having uh, higher amount of daughter isotopes if you have a high samarium neodymium isotopic samarium neodymium elemental ratios, because this elemental ratio is important. That ultimately determines how much uh, daughter isotopes are produced. You can remember the rubidium strontium ratio, the similar rubidium strontium ratio also, right? In the decay equation, we have this ratio, right? Remember? So similarly, it is important. So garnet, some important materials that we are frequently using in geology in isotopic systems, because for age dating like aspects, garnet is a good grain for samarium neodymium system, because they contain fairly large amount of both samarium and neodymium, right? Because I think you can remember we discussed in advanced igneous petrology about the partition coefficients, right? So for garnet, partition coefficients are usually higher, relatively higher for these rare earth elements, especially for heavy rare earth elements, right? But samarium neodymium lying in this middle area, they also prefer to go into garnet when they form, right? So therefore, garnet can contain a lot of, especially samarium. A lot of samarium can be there because it's more towards uh, the right hand side. That means towards more into what the compatible side. Okay, because garnet prefers compatible elements, right? Heavy earth elements are very much concentrated in garnet. So this is, although it's a kind of middle, but samarium relative to neodymium will be preferentially partitioned into garnet. So therefore, with time evolution, samarium will decay, uh, forming high amount of daughter isotope neodymium in garnet. Okay, so that's why garnet is used for age determinations in samarium neodymium isotopic system. So you can see here. One thing I think I don't know whether I mentioned during rubidium strontium isotopic system about mica, right? Similarly, mica prefers a lot of strontium, a lot of rubidium, sorry, a lot of rubidium. So therefore, if we collect a lot of mica and use them, we can find a lot of strontium isotopes, right? Strontium is rubidium decays into strontium, so strontium is accumulated a lot in micas. So like garnet, which contains a lot of neodymium, right? So remember for rubidium strontium dating, you can just note if I haven't mentioned it at that time, micas are preferentially used in rubidium strontium. Okay, so garnet is used in samarium neodymium system because of this feature. In mid-ocean ridge basalts, you can see a less amount of ratio. I mean, lower ratio is there, 0.32. Seawater further low, and shale it's 0.2. The ratio is 0.2. Very similar, almost similar to the seawater, because these are in equilibrium most of the cases, because the sediments are in equilibrium with seawater. A lot of sediments are deposited in ocean floors. If you take the carbonates also, they will show you very close to these values. Okay, and solar system. What is it? The planetary bodies, our solar system in general as a whole contain like this amount of samarium neodymium ratios. So as we mentioned before, this ratio matters. Okay, the samarium neodymium ratio matters, right? So if you have a high samarium neodymium ratio, what happens? You will end up with more neodymium, right? Because samarium decays into neodymium. So you will get a lot of daughter isotopes. And if you have low samarium neodymium ratio in a rock, with time it will evolve for less neodymium isotopic composition, right? So this is exactly opposite to the rubidium strontium system, because here the parent daughter behavior is different from rubidium strontium parent daughter behavior. Okay, do you understand this note? This one I already explained. The parent samarium isotope element, the parent samarium element will be enriched in depleted sources. What are the depleted sources? Do you remember we talked about depleted mantle, right? So mob depleted. So all these are depleted sources. Okay. Why we call depleted sources? They are depleted compared to the continental crust. Okay. They are compared to the continental crust. Only we consider these depleted material. Okay. Right. So the mantle products are always depleted in terms of incompatible elements. So normally, if you refer some material which is depleted, that indicates depleted in the sense of incompatible elements, right? Normally, continental crust is enriched. We call it enriched. Remember, always we talked about continental crust is enriched. Why enriched? It's enriched in incompatible elements. So rare earth elements as a whole, okay, rare earth elements as a whole, they are incompatible, right? We mentioned it already here, right? So therefore, continental crust is no always enriched in rare earth elements or incompatible elements, whereas the mantle or the depleted mantle and their products like mob are always depleted. They are always depleted. So that's why you see a big gap in compositions, right? there is a big gap in composition when you talk about these products. So anyway, the samarium is less incompatible compared to neodymium, right? Remember, because neodymium prefers more melt. Neodymium prefers more melt. Okay, so it is more incompatible, right? So samarium is less incompatible. So if something is less incompatible, that means it prefers more residue, right? It prefers more residue than melt. So if you have residue and melt as a result of melting, uh, more compatible ones will like to go to residue. More incompatible ones will like to go to uh, melt, right? So if you compare samarium and neodymium, what is more incompatible? In samarium and neodymium, what is more incompatible? Neodymium, right? Neodymium is more incompatible. Therefore, a lot of neodymium will be accommodated in melt, and less amount of samarium will be there. Okay, but in the residue you will have lot of compatible. That means samarium will be enriched in residue because it is less incompatible compared to melt. So therefore, with time, what would you expect for the residue? With time, what would you expect for the residue if you have high amount of samarium, right? Because it is more compatible. It is that prefers much residue, right? So with time, if you pass time, let's say time t, right? Some duration of time, right? So during this time t evolution, what would you expect in terms of neodymium isotopic ratios? Since you have a lot of samarium, you will definitely have a lot of samarium neodymium ratios. So that means it should be like these high samarium neodymium ratios, and it will definitely result more neodymium isotopes, right? So more daughter products, right? So that means with time, you will have high neodymium isotope ratio for the residue. Remember, for the residue, you will have high neodymium isotopic values because you have more parent material available in that residue during this formation, right? So the melt produced will have less amount of samarium and more amount of neodymium is there, but neodymium will remain as it is, right? Because it does not decay to anything, right? It does not decay anything, right? But whatever the samarium you had will decay, right? Samarium will decay to form radiogenic neodymium. Okay, this is not radiogenic neodymium. This is the initial neodymium. Neodymium just incorporated there, not the radiogenic product. To make anything radiogenic, radiogenically produced over this t time interval, then you must have some samarium. So a little amount of samarium was there relative to the residue here, because samarium was less incompatible in melt. So therefore, at the same time duration, like here, the same time duration, you will have less neodymium isotopic ratio, lower neodymium isotopic ratio compared to your residue. Okay, so if suppose here you have isotopic ratio of neodymium 0.5, it should be after t time interval by decay of existing samarium. Here, after the same time interval, you will have something like 0.2 or 0.3 or something like, anyway lower than the residue. Okay, so always remember, in neodymium isotopic system, residue will show high value of neodymium isotopic ratio, because in a residue you will have a lot of parent isotopes accumulated. That means samarium accumulated there. So a lot of samarium will decay, producing high neodymium isotopic ratios, daughter isotopic ratios over time, right? During the evolution, this happens. So in the case of residue here, okay, in the case of residue, I put R there, you will have more neodymium isotopic ratios. And in the case of melt, you will have less neodymium isotopic ratios. Okay, this this feature is there for the samarium neodymium isotopic system. So now we consider partial melting of the mantle, and partial melting of the mantle produces continental crust. Okay, so continental crust is representing what? The melt composition. So for example, the melt, the continental crust. If you see the continental crustal neodymium isotopic composition and compare it with the mantle residue isotopic composition, because mantle is a residue, a depleted mantle is a residue after formation of the continental crust, right? Remember, residue will have higher amount of neodymium according to our explanation, right? See, residue will have high amount of neodymium isotopic composition. So unlike rubidium strontium isotopic system, if you analyze a mantle sample, that means a residue sample, you will definitely see high neodymium isotopic composition in mantle samples compared to continental crust. So that means in the continental crust, neodymium isotopic composition is low. Okay, right. So this thing you have to keep in mind. So continental crust being enriched in incompatible elements, yet has low neodymium isotopic composition compared to the residue or compared to the mantle. Okay, so in the sense, the usage of this depleted term in samarium neodymium isotopic system, you remember the higher the isotopic neodymium there, it is more depleted, right? In terms of samarium neodymium isotopic system, remember, because the mantle we consider as a depleted product, so that's why we see this type of behavior, right? But in the case of samarium neodymium isotopic number, this is just the number only, okay? Just the number, the value only, right? If you want to say something is depleted, that means you must have a higher neodymium isotopic value. Okay, if you have a high neodymium isotopic ratio, means that material is more depleted, which is opposite to the rubidium strontium isotopic system. Remember, rubidium strontium isotopic system, if something is depleted, what did we mention? Low strontium isotopic ratios, right? That's why the mantle had low rubidium isotopic strontium isotopic ratios. But being samarium neodymium isotopic system is opposite to the rubidium strontium isotopic system. If you want to say something is depleted in neodymium isotopes, you have to see high values of neodymium isotopic ratios. Okay, if neodymium isotopic ratios are low, that means it is enriched. Okay, so the continental crust will be enriched in neodymium isotopic system. That means you will have high ratio. Sorry, the number you will have something like, for example, just you put number like 0.2 for the continental crust, right? 0.2 for the continental crust and 0.5 for the mantle. These are not the correct values, but I am just putting some numbers to give you the idea, right? Like here, right? We put 0.2 here for the melt. We put 0.5 here for the residue, right? So residue is the mantle, right? Residue is the mantle here, and melt is the continental crust, right? So melt has low isotopic neodymium values. Residue has high isotopic neodymium value, right? This is just the number, right? So we will see this in a diagram later on, and see how they compare, how they can be compared with the strontium isotopic system also. Then you will realize it, because I will be showing you in x-axis rubidium strontium system and y-axis samarium neodymium system. So in that case, you should be able to remember that diagram, and then you can understand this very easily. Okay, so I will just put a very small diagram here, just a schematic diagram, so that you can remember this phenomena. Okay, so I put here neodymium isotopic ratio, right? One neodymium isotopic ratio is what is it? 143 neodymium, right? That is the radiogenic product, 143. And I put rubidium strontium in the x-axis. So rubidium strontium system produces strontium 87, right? Strontium 87. So if you want to, if you analyze both continental crust and mantle sample, right? If you take a mantle peridotite and a continental crust sample like granite, what would you expect in this plot? Where will they plot? Okay, let's put first the continental crust. Continental crust, how would we expect the strontium isotopic composition? It should be high, right? It should be high. Why? Because strontium is produced by rubidium. Rubidium is more incompatible, and in the continental crust, lot of rubidium is there. So over the time, it will produce large amount of strontium isotopes. So therefore, strontium will be enriched. So enriched means, let's say somewhere here, right? Some value like here. Let's put for strontium. And what would you expect for the neodymium for that continental crustal material, granite that we are talking about? It should give you a lower value, right? Remember here we mentioned it should be a lower value. So definitely it should be a lower value than something lower. Strontium should be higher, right? Then you can have a value like, I mean, you don't need to put any correct numbers. Just put like here, right? Low neodymium and high strontium. Low neodymium and high strontium, right? So if you take a mantle sample and analyze, definitely you will see low strontium value. So low strontium value means maybe you have to go some value like here, right? Low strontium value. And what about the neodymium in mantle, right? It should be high, right? Neodymium, because it is a residue. So then your neodymium should be high. That means you will end up with somewhere point like here, isn't it? Compared to the continental crust. So then if you just make this diagram, this is the mantle and this is the continental crust. Okay, so you will see this difference. High strontium, low neodymium. Look here. High strontium, low neodymium for the continental crust. But for the mantle, high neodymium, low strontium. Okay, high neodymium, low strontium for the mantle. Because mantle is the residue, continental crust is the melt. So this is the opposite behavior you can expect for these two isotopic systems, right? So if you want to show that in a combined isotopic diagram, that is neodymium strontium isotopic diagram, right? This is what we showed here. Okay, So you will see this type of a difference. So always remember this difference. Okay, mantle lies above always in neodymium, but for strontium it is low. That's why you are having some value like this, right? For the continental crust, it is always high in strontium, but low in neodymium, right? So this type of positions will be there if you plot them together, right? So remember this entire plot, this schematic entire plot. You can remember this one just to understand the difference between these two isotopic systematics. Okay, right. So I hope you got the point. Did you? Do you have any question? If you have any question, please ask, because these two are very opposite. So therefore, you must remember the difference.